Okay, I am mostly going to want you guys to work through these questions by yourself, but let me just read the question first. You'll get a chance to attempt the question, and then we'll mark it together. Okay, so question 8.1 reads, in the diagram, MP is the diameter of the circle at center O. MP cuts the chord NR at T. The radius NO and chords PR, MN, MR are drawn. Angle R1 is equal to 69 degrees. Okay, so angle R1 is 69. You can see they filled it in on the sketch. There's a radii, or there's radii. There are chords and other important things mentioned in the paragraph there. Go read it again if you, and then highlight, I guess, or jot down the important parts of that. Let's move over to the questions now. So determine, giving reasons, the size of angle R2, O1, M1, and M2 if it's further given that NO is parallel to PR. Okay, I'll give you guys about 6 to 7 minutes to finish this. It's really not a lot. You just need to write down your answer combined with your reason for each question. Okay, I think for the last question, you're going to need 2 answers and 2 reasons, or at least before you get to M2, there's first another angle you need to work out, also giving a reason, and then you get M2. Okay, so go ahead and do that. I'll give you like I said, 6 to 7 minutes.
So can you go put up, please, so we can.
So for the first question, we need to calculate angle R2. That is this angle over here. So how to do this? Okay, the first thing that I'm noticing is that MP, being the diameter, subtends a 90-degree angle. Okay, and because this entire angle is then 90 degrees, we can subtract the 69 to give us the angle R2. So R1 is 69, so then R2 has to be 21 degrees because they are complementary angles. They add up to 90. Okay, so I would actually, before writing down angle R2, I would first state that the entire angle R, so basically MRP, angle MRP is equal to 90, and then I'd state my reason, which is angle in a semicircle. And only after I've written that, then I now state that angle R2 is equal to 21 degrees. But I guess writing angle in a semicircle for this one is also fine. Yeah, because it's not that you're saying R2 is 90 degrees, R2 is 21, but the fact that the entire angle is 90, it means we can subtract the 69 to get angle R2. So we're still using the reason angle in a semicircle. Okay, can I just hear who found angle R2 a different way, perhaps? Maybe using some other method. There's lots of ways to find it, but I just want to know what was your preferred method if you did get it a different way. Okay, so I assume everyone then got it this way. Let's try for angle O1. Okay, so O1 is a bit more easier to see, I would say, because it looks exactly like the theorem, which says angle at the center is equal to 2 times angle at the circumference. We're so used to this shape already that we can easily spot the answer there. And so we just times the 69 by 2, and then that's our answer for angle O1. So I guess it's going to be 138 degrees. your reason angle at center is equal to 2 times angle at circumference. Okay. So angle O1 is equal to 138 degrees. We just double the 69. Okay, so it's important that we know all our circle geometry theorems to answer these questions. All right, let's have a look at the next one. Angle M1. Now, remember they said that NO is a radius, but OM is also a radius, which means we have radii, and radii are equal. And so we are basically forming an isosceles triangle in OMN. OMN is an isosceles triangle where angle O1 is equal to 138 degrees. Okay, so the remaining portion of the 180 just needs to be split in half. And so how we calculate that is we say 180 minus the 138. I think that's 42 degrees. And we split this in half. So divided by 2. And if I'm not mistaken, I think this is equal to 21 degrees. 21 degrees. So N1 is also 21. M1 is also 21 degrees. Okay. Now that I'm thinking about it, I didn't have to do this. There was another way of looking at it as well. I could have also just used the butterfly theorem or the bow tie theorem, whichever you refer to this one as. I'll highlight the parts I'm talking about now. M1 is 21 because R2 is 21. Can you see it's that bow tie butterfly thing? So the reason for this is angles in the same segment. So you could have also even used this theorem. Okay, the moment you see a bow tie or a butterfly, you're allowed to use the angles in the same segment theorem. Is there someone who got to this angle a different way? Maybe not using the radii or not using the angles in the same segment. Okay. If not, then we'll move on. So the next question was for us to work out angle M2. Given that NO is parallel to PR. Okay, so this question was now 4 marks, meaning that there's a couple of things that we probably have to do here. Sorry, there's someone trying to get in the Zoom meeting. Let me just add that person. Okay. Now, to continue, angle M2. How can we work out angle M2? Josh, can I hear by you? What did you do here? How did you work out angle M2?
So by O2, that's gonna be 42 because O1 is 138. So you can say supplementary angles. And then P is gonna be 42 because of alternative angles. And then 90 plus 180 minus 90 minus 42 will give you M2.
Well done, well done. Okay, so just to explain to everyone also what Josh is saying, he started with angle O1, which we already calculated in a previous question. That was 138. Okay, so now if you look at these angles on a straight line, if O1 is 38 or 138, then O2 would be 42 degrees, angles on a straight line. And now another thing we are taking into consideration, that NO is parallel to PR. NO is parallel to PR. So if these lines are parallel, it means that angle P is also going to be 42 degrees. These are alternate angles. Okay, so you have angles on a straight line, then you have alternate angles. Now we look into this triangle PRM. Triangle PRM. Remember angle R, the whole angle R is 90 degrees. Then angle P is 42 degrees. We just calculated that now, that was alternate. You can then work out angle M2 as 48 degrees. They all should add up to 180. The 48 plus the 42 plus the 90 should add up to 180 degrees, interior angles of a triangle. Okay, brilliantly done. And this is basically the easy part of the circle geometry. It's just to get you into the groove of doing the Euclidean. So let's move on to the next question, which is going to be definitely a little harder than this one. So let's read question 8.2, some more circle geometry. But like I said, this one is going to be a little bit more harder. 8.2. In the diagram below, ABCD is a cyclic chord. AB, DC are produced to meet at E. They are not tangents. Often I get asked, with these long lines extending through the circle, are they tangents? No, they are not tangent. A tangent only touches the circle once, and these lines clearly cut the circle at 2 points, A and B, and then again at C and D. That's the other line. So they are not tangents. They're just chords that is being produced all the way to point E. Okay. Right, something produced meet at F. Okay, I see that. Then angle AFB is equal to 2x, and angle DAB is equal to 3x. Okay, so angle F is 2x, and angle A is 3x. Angle E is x. All right. The first question is, the only question for 6 marks is determine the value of x. So this means that we can find x in terms of degrees. Okay, no other information is given besides that ABCD is a cyclic chord. I don't see any other useful information there. So I'm just going to zoom in on the sketch and then let you guys attempt this question. Calculate the value of x. Melo, would you like to tell us how you got to your answer? First of all, your answer is correct. X is equal to 20 degrees. But how did you get to that answer?
Oh my days. Oh yo, sir. So I started by saying C3 is equal to 3x exterior angles of a cyclic quad. Wait, are you gonna write it down on the circle, sir?
Okay, let me write it out. So that's 3. Wait, not that one.
C3.
Angles C3, yes. Okay.
Yes, sir. And then I said D1 is equal to 180 minus
5x.
Brackets. Yeah, 180 minus 5x. And then I said D2. So you know angles on a straight line. So D2 is equal to 180 minus 180 minus 5x, which just left me with a 5x. Yeah, left me with a positive 5x. So and then I use triangle AED because they have all the x values and all those x values equal to 180. So and then I said 3x plus x plus 5x is equal to 180. And then that got me to 9x. 9x is equal to 180. And then I divided both sides by 9. And then I was left with 20 degrees.
That is correct. Well done. I also got this answer. I did it a completely different way. Well, not a completely different way, I lie. It's the same way, but just using different triangles. Yeah, so well done. Okay, can I just walk us through it quickly again? So we start here with this angle A, which is equal to 3x, that was given. Then we said that angle C3 is also equal to x because it's the exterior angle of the cyclic chord. Okay, so ABCD is a cyclic chord. A and C are opposite each other. So A is equal to the opposite exterior angle. Okay, so C3 is 3x. We also know that F is 2x. So if C and F is 3x and 2x respectively, then D being the third angle, but the exterior angle of the triangle, it's equal to 3x plus 2x, which in this case is 5x. Okay, now we look into the big triangle, ADE. So A is 3x, E is x, and D is 5x. If you add them up, you get 9x, which is equal to 180. So you divide by 9, x is equal to 20 degrees. This is all correct. What you need to do now is just add your reasons in for everything. Okay, so exterior angle of a triangle, we started, no, exterior angle of a cyclic one, sorry, they are equal. And then exterior angle of a triangle, that's the 5x over here. Or like how Melo did it, is he first calculated the interior angle, which was 180 minus 5x, and then he got this angle as 5x. Angles on a straight line, that's also fine. And then you use the interior angles of the big triangle, the red one. Nice.
So can I ask something?
Yes.
So would you have been able to use the small triangle CBE?
Yes. How did you do that with a
No,
small
so
triangle?
I'm just asking, like, because that's what I saw. I didn't see the bigger picture. So
Yes.
I thought C1, I thought A was equal to C1, right? And then then my only problem was finding B1. So that was my only problem.
Okay, so come and
And I
find
know.
B1.
Okay.
So
okay.
C1 is 3x. C3 is also 3x because they're vertically opposite. You see that? Okay. I would say that angle, well, I'm going to do it the same way that Melo did it. I'm going to say D2 is equal to 5x because like it's the exterior angle of this triangle. See this triangle? So that's 3x, this is 2x, that gives us 5x. And then what do I have to do now? Okay, so if this is 5x, then the one opposite it will be 180 minus 5x, which then makes this one, the exterior one, 5x. So angle B1 is equal to 5x. And then you can just do, yeah, then you just work with those interior angles there.
Okay. Thank you, sir.
That's also how I looked at it. Why did I do it differently? Where did I get a 4x from? Somehow I got a 4x. I also got to 20 degrees, but I said somehow I calculated the angle B2 as 4x. It is also true. I don't even know how it, oh, see, the thing is I got angle D1 as 4x. But then again, I don't even know how I did that. I didn't write down my reasons here, but somehow I got D1 as 4x, and then I got B2 as 4x, and then I used, I used that geometry to calculate x is 20. But yeah, let's move on to the next question. Now, in the diagram, M is the center of the circle. A, B, C are points on the circle such that AC is equal to BC. Then the line PA is a tangent to the circle at A. PQ is drawn, parallel to CA to meet BA, whatever. Okay, and Q is equal to X. That's the important part. Q is equal to X. There's a tangent. Where's the tangent now again? AR, I think. Can we confirm that? No, PR. PA, sorry. PA is a tangent. Can I just highlight it? There we go. Okay, don't confuse that with AR. AR is not a tangent. It's PA, that's a tangent, or AP. Okay. Then they say PQ is drawn parallel to QP. We can see that it's already in on the sketch. Also, AC is equal to BC. Yep, that's also mentioned. And then they say M is the center of the circle. So as you can see, if M is the center of the circle, AB is then not a diameter. AB is not a diameter because it doesn't pass through the center of the circle. Okay. So you can't just assume that angle C1 is 90 because that line does not pass through the center of the circle. Okay. Now, angle Q is equal to X. The first question is for us to determine 4 angles also equal to X. So they already give you Q as X. Find 4 other angles equal to X and state your reasons for that. Again, I'll give you 4 minutes to do this. Okay, let's answer the question. I'll start with highlighting the information that was given first, and then we'll find the 4 angles and then do the second question also, which was to prove that ABPR is a cyclic one. So I'll start with the parallel lines. AC is parallel to is that QP. That's the first thing that was given. Also, they also said that line AC is equal to line BC. And then also they gave us angle Q as X. Okay, so we're going to use these things to, I guess, calculate 4 other angles that's also equal to X. Now, I'm first going to start with the corresponding angles. So I'm using my parallel lines to produce corresponding angles. So angle A1 is equal to angle Q because they are corresponding angles. Notice this is the F in the parallel lines. You know, those 3 principles: corresponding, alternate, and co-interior. That's the F. Okay. Then also, because BC is equal to AC, we have an isosceles triangle, which means that angle B is now also equal to X. I think, what's the reason we can give there? It's angles opposite equal sides. Okay, so we're not allowed to use the word iso. We're not allowed to use the reason isosceles triangle anymore. So we need to write down what the definition of an isosceles triangle is, and that is the angles that are equal. The angles that are opposite the equal sides. Yeah. So if it's opposite equal sides, then the angles are then also equal. So we use the parallel lines. We also use the equal lines. Now, the next thing for me to use is the tangent. Okay, so the tan chord theorem says that an angle between a tangent and a chord, which is this angle here, angle A2, it's equal to the angle that is being subtended from that chord. Okay, so this might have been the angle that you guys you missed, or maybe found lost, because obviously it's a much harder one to see. So angle between a tangent and a chord is equal to the angle subtended from the chord. We normally just shorten this to say tan chord theorem. Okay, we don't write the entire theorem down. As mathematicians, we are lazy, so we kind of just, you know, shorten all the theorems to like a handful of words or symbols if possible. Then lastly, since A2 is now X, we can use this lines again and form alternate angles. So that means that angle P is also X. Okay, so how many angles is that now? It was A1, that was corresponding. Angle B, that was the isosceles triangle. Then A2, that was the tan chord theorem. and then angle P. This last one was alternate angles. Okay, so that's 4 angles in total, and that's what they wanted me to calculate. Cool. The next question says, prove that ABP R is a cyclic chord. So this shape that I've highlighted now, prove that that is a cyclic chord. Now, a cyclic chord doesn't have to connect. I don't need to connect AR and BP to make it a cyclic chord. I can just leave it as an open cyclic chord like this, but then I just need to prove that the angles in the same segment are equal. So the corners of the bow tie, basically. If I can prove that angle B is equal to angle P, then I know this is a cyclic chord. So there's no proving that needs to be done because we already calculated that B and P are both X. So I'm just going to state now, angle B is equal to angle P. They are both equal to X. This was already proven. So therefore, ABPR is a cyclic chord. The reason for this being the converse of angle in the same segment. Angles in same segment. Okay, and that's it. So whenever you're proving a cyclic chord or proving a tangent or anything really about proving, we normally make use of this phrase converse, which says that we are reversing the theorem. The natural course of the theorem is when you say this angle is equal to that angle, but now the angles are already given and we are using the angles to prove that there's a cyclic chord. So it's reversing the theorem. Okay. Let's move on to the next one. Right. Prove that BA over BQ. I'm reading this last question here. Prove that BA over BQ is equal to BC over QR. BA BQ BC QR. Okay, I'm going to highlight the lines they are referring to. BA, then BQ, BC, and then instead of saying BR, it rather says QR. It rather says QR. Now, the reason why it would have made sense if it said BR is because I'm looking at the proportion in this triangle, the proportional theorem. So let me highlight the big triangle so you can see what I'm talking about. Notice in that triangle, there's these parallel lines, which creates the proportional theorem. Okay, so we can say the short line BA over the long line BQ is equal to this short line BC divided by the long line BR. Okay, but now instead of them using line BR, they are using line QR, which kind of stands to reason that if the proportions are the same, it must then mean that BR is equal to QR. Now, is that true? Is angle BR equal to angle QR? If you say so, what's your reason? Are these two lines equal? Yes or no, and why? So basically, this angle Q here is X. We also proved angle B equal to X. So since they are equal, we can say that therefore QR is now equal to BR. because it's the converse of the isosceles triangle. So we say converse, angles, opposite, equal sides. Okay, now that they are equal, let's write down a proportion for the big triangle. So we are looking at triangle BQR with line AC being parallel to line QR. Okay, so we now say BA over BQ, and this is equal to BC over BR. This is the proportional theorem, prop theorem. Let's also not forget to state which lines are parallel. AC parallel to QR. Okay, this is how you write everything down. It's so important that you write all of this down. And now we say, but since QR is equal to BR, we can then just substitute the BR with a QR, which means that therefore BA over BQ is now equal to BC over QR. And that's your final conclusion. Okay, so where do you get marks? First of all, you get marks for this converse theorem, then a mark for the proportion, and then also for the reason of the proportional theorem. So that's the 3 marks you get. Obviously, you won't get the mark for this final answer because that part was given. Okay. But you need to write this statement here, you know, where you're speaking about this thing that you stated. QR is equal to BR because the converse of angles opposite equal sides. So it's the reverse of the isosceles triangle. Yeah, so it's nice and easy to, I guess, do the work. None of this I didn't feel difficult yet, but I guess the difficult part is writing all of it down. Yeah, let's do our last question. Oh, I see it's already 10 o'clock. Can I just find out, is it possible for us to do this last question, or should I rather give you this to do as homework? Could we continue for this last one?
All right, it's fine by me, so.
Okay. If you need to leave, you can leave, but I'm just going to do this last question and then we're done. It might take us 10 minutes or less. Right. Question number 10. In the diagram, TSR is the diameter of the circle, of the larger circle, having center S, okay? Chord TQ of the larger circle cuts the smaller circle at M. PQ is a common tangent, so there's a tangent to both circles at PQ. RP is perpendicular to PQ and MS is parallel. Okay, now everything that they have mentioned there on top is all indicated on the sketch. We can see the perpendicular lines. We can also see S being the center. Then also MS is parallel to QR. Okay, so that gives us like a proportion in this in the circle, right? There's a triangle which we can say the ratio for that length to this one would be the same for this length to that one. Okay, that's probably going to come in handy later on. Now, let's read the first question. Prove giving reasons that SQ is the diameter of the smallest circle. SQ is the diameter. Okay. This line here, we need to prove that it's the diameter to the circle. Now, I'll start with this. Where do I start? Okay, let's see quickly. We want to prove the tangent chord. No, we want to prove that it's a diameter. So I'm assuming that we need to prove this angle, M2, is 90 degrees. If I can prove angle M2 is 90, I know that it's a diameter. Another way to prove a diameter is to prove that this line is perpendicular to this line, because diameters are perpendicular to tangents. So those are the two things that I'm looking to prove now. Okay, it was much simpler than I thought. It's 3 marks, but it is actually very simple. So what we're supposed to do here is SQ or S, sorry, is the center, right? S is the center of the circle, which means that SQ is a radius, and a radius is perpendicular to a tangent. So if SQ is the radius of the big circle, that would be perpendicular to the tangent. Now remember, this radius of the big circle is the diameter of the small circle because it's also perpendicular to the tangent. Yeah. And so that's your reason basically. How do we write this out? We'll start off by saying that angle Q2 is equal to 90 degrees. Radius perpendicular to tangent.
Mustn't we say SQP because Q2 goes to R? So it
Thank you, yes. You are right. SQ is only that fraction of the angle. But SQP, thank you, SQP, we must be specific there, is equal to 90 degrees, radius perpendicular to tangent. And then we say, therefore, SQ is a diameter for the small circle of the smaller circle. Smaller circle. Now we're also going to make use of the word converse because we are reversing a theorem. We are reversing the theorem diameter perpendicular to tangent. Okay. Right. Diameter perpendicular to tangent. So we use the radius, SQ being the radius of the big circle. And because it's perpendicular, we then also can say that SQ is then a diameter for the smaller circle. Okay. Let's just answer our last question for today. Right. RT is equal to RQ squared divided by RP. RQ squared. Okay, this is maybe not going to be such an easy question again, but if I cross multiply this expression, I'm going to get something like RT times RP is equal to RQ squared. Now this looks like one of those proportions that we get from similar triangles. If you use two triangles that both has the line RQ in it, you can end up with a proportion that looks like this, which we then can write like that. Okay, so the goal here is to find two triangles that has the line RQ in it. So two triangles with the line RQ, and hopefully those triangles also have the RT and the RP. RT and RP. So RT is this line here, the diameter of the big circle. That's RT. RP is the short line. So I'm assuming we're going to be using this triangle, RTQ, and then the small triangle, RPQ. So RTQ or PQ, because both of those triangles has the line RQ in it. And I guess that's how we're going to get the RQ squared. And then also, both of those triangles has the, or either those triangles either has the RT or the RP in it. And that's how we're going to cross multiply to end up with that expression. Now, before we start our similarity, let's just write in triangle RTQ and triangle RQP. Okay, hopefully I've named them correctly, but let's see. So you need to prove at least two angles are equal. The third one will then automatically be equal. I'll start with angle T. I'm going to say angle T is equal to angle Q3, because that's the tangent chord theorem. Q3 is the angle between the tangent and the chord, and angle T is the one that is being subtended from the chord. Okay, the angle there. So this is the tangent chord theorem. Tan chord. And can you see that I wrote both angle T and angle Q in the middle? So they are proportionate there in the naming of the triangles as well. Then angle P, can we see that angle P is 90 degrees, right? They said RP is perpendicular to QP, so it's 90. Also, we know that angle Q, this whole angle Q, well, not the whole angle Q, but rather PQR, that angle is also 90 degrees because it's the angle that's being subtended from the diameter. Okay, the line that passes through the center, it's being subtended there at the, or the angle is being subtended at the circumference, giving us a 90-degree angle. So we have two angles that are 90 degrees. Angle P was given as 90, and angle Q, we calculated now. Let's not just say angle Q, let's say angle PQR. So that's also 90 degrees. Our reason here was angle in a semicircle.
So do you not mean TRQ, sir, or MQR? Because the angle that you've indicated, I think that's not the 90 degree.
You are correct. Yes, thank you.
It's okay, sir.
Yes, it's TQR. I can't see the letters. I was guessing wrong now. I was thinking it was T. I mean, thinking it was P, but it's actually T. So TQR, that's correct. So both of them are equal to 90 degrees. P was given. TQR is 90 degrees because it's the angle in a semicircle. Now, we don't have to prove the third one, but the third one is just the third angle of the triangle. So I'm just now going to say, therefore, triangle RTQ is now similar to triangle RQP. Reason being the three angles of a triangle. So angle, angle, angle. Okay, we're not yet done. We need to now still write out the ratio for these triangles. Okay, so I'm going to do it here in the corner. It's very messy. but let's try and do it. So it's RT over RQ. You can see now I'm taking the first two letters, RT being the first two letters here and RQ being the first two letters there. And this is going to be equal to, now I take the last, the first and the last letter. So it's RQ and RP. RQ and RP. Again, the reason I'm choosing these specific ratios is so that both ratios can have an RQ in it. Okay, so you see I have an RQ and another RQ. Once I cross multiply, I'm going to end up with an RQ squared, and that's exactly what they asked me to prove. So now I get RQ squared, and this is equal to the RT times the RP. And so now if you just wanna write it like how they had it, you just divide by what was it that we had to divide by? But yeah, you just divide by that thing and then have it written in the way how they want it to be. Okay, thanks guys. This lesson ended off very messy, but at least we got some nice practice on circle geometry and similarity and some proportionality also in between.
So what's the theorem that we stated at the end? Perpendicular from right angle vertex to hypotenuse.
No. For that final, for the ratios that I wrote.
And also then when you say, oh, I see what we did. Okay, it's fine. So
yeah, we were just using the similar triangle. So your reason there is ratios. No. Let's say proportion in similar triangles. Proportion in similar triangles. Okay, so that's how we took the first two letters of each triangle and the first and the last letter of the two triangles. That's what I did.